Hello, my name is Kaylin Cummings, and today I'm going to talk about Lab 2, Projectile Motion. Today we'll be reviewing Introduction to Models, Coding, Discussion, and Conclusions. The purpose of this lab was to visualize projectile motion and apply Newton's second law. This was achieved through tracker coding and physics models, and we could tell that projectile motion was indeed present. The first law we'll observe is Newton's second law. This law states that the net force is equal to the product of mass and acceleration. As can be noticed, we can also claim acceleration is equal to net force divided by m. We will use this to, of course, determine net force. For F net, we have two expressions. Without drag, the net force is impacted in the y direction only. The expression below shows us taking drag into account by including the addition of negative b, which b is the drag constant, times velocity squared, also times phi hat. Here are the models key for projectiles in our experiment. We will use the position update to find our positions with the goal of receiving the ultimate final position. Our next component to acknowledge is velocity. Velocity is equal to the displacement over time. This is how we calculate initial velocity. To update velocity, we use the update formula shown below. We use this as it allows us to update positions. This model is the kinematic equation. It is often used in solving projectile motion problems. We view this formula later on in the experiment upon discussing what-if-type scenarios. Below this, we have visual of basic projectile motion, appearing like an arc. In this experiment, both system and surroundings are present. Our system is the crumpled paper ball, being the experiment and force focus. Our surroundings include that which is not the system. This includes the table, meter stick, cup surrounding, etc. Our first initial condition to discuss is actually a constant condition. This is the crumpled paper ball's mass, which is 4.5 grams. We also determined the initial position through tracker at 2.924 e negative 4, 2.6660 e negative 3, 0 meters. To determine initial velocity, we viewed initial displacement over time. Therefore, we subtracted our beginning position from that which took place 0.033 seconds later. Then we divided this displacement by the time of 0.033 seconds. This is how we calculated drag. We used the formula given to us, and from here, we calculated the change in momentum. We use this change in momentum to give us the F drag in the x direction. We then use this F drag in the x direction and manipulated the equation to find B. Overall, our experimental details include our object of focus, which was a crumpled ball of paper, what was viewed, which was the paper being tossed upwards, how was the data analyzed using tracker and glow script coding, and what did we notice, which was projectile motion. The first two components of the code on the left contribute to the visualization created. The next component contributes to the charts and plots created. The coding on the right introduces our initial and constant values. The ball mass up top is constant. Below it is its initial position from tracker, and below that is calculated initial velocity. Next, we have the constant starting time and change in that time constantly for delta t. We then provide gravity's constant and the drag constant as calculated earlier. Here's our code's while loop. We start our calculations with net force. This is for acknowledging drag. The code for that which is not acknowledging drag would differ as it would lack the bulky addition component of drag force. Next, we use velocity update and position update to determine position. We then add the change in time to the initial time to get the concerned time. The next two parts of the coding contribute to our plots created. Finally, we end the loop in coding with the print commands. Here are the plot coding results for the calculations not acknowledging drag. Shown are the charts focusing on position and time and velocity and time. There is also a chart concerning the object trajectory. Here are the plot coding results for the calculations acknowledging drag. These charts are concerning the same topics as the other. At the top, we have the observed position changes. Next to this is a graph focusing on the positions and motion observed. Below are the results of the coding graphing using sheets. These graphs also focus on positions and motion, but calculated using coding. The left show results of that which is not including drag. The right results acknowledge drag. There were similarities and differences present between the results acknowledging and not acknowledging drag. What was the same was the general shapes of mostly everything in the plots. However, what was different was the velocity in the x direction with drag as well as the distance traveled. This distance traveled was slightly farther in the y direction for that which was including drag, while it was slightly farther in the x direction for that which was not including drag. There were also similarities and differences for the real versus predicted graphs. All graphs have similar x-related values. Though they may have differed slightly, it was not by much. However, the calculated or predicted y values differed greatly from that which was observed. Unlike the observed values, the calculated y values eventually became negative. There are many possible errors which could have taken place during this experiment. One of these possible errors is tracker misuse, as we are not very experienced with the app. Another possible error is poor video quality. I think this may have been a big error for our group, as our video could not be edited to where the motion after the ball hit the ground was cut out. Another possible error is improper motion. This ties into the last point, as we were not supposed to video what happened after the ball hit the ground. The what does it mean question concerns terminal velocity and questions if it's present. It is not present. We see this in the figure on the side. We can notice that the slope at the end does not trail off and become zero. Therefore, we know terminal velocity is not present, as terminal velocity is only present when the force of gravity is equal to drag, or when the net force is zero. The what if question concerns the way in which the ball was tossed. What if the ball were instead thrown straight up? If it had the same initial speed, would this object take longer to reach the ground, the same amount of time, or shorter? It would not remain the same. We view the kinematic equation here. Aside from time, F net is the key component changing. Without drag, the force is key impacted in the y direction, being negative mg. However, acknowledging drag, we have our force of gravity as shown above with the drag force added. The increased y values would increase v hat, thus increasing the drag force and thus the time it would take to reach the bottom. Therefore, saying time would increase and not remain the same.